Okay, hello everyone. This is part 2 of this year's Nirenberg lecture in geometric analysis. The speaker for the part 2 is Antoine Schoen from UC Berkeley. Antoine obtained his PhD in 2019, and he obtained a very strong and resolve a long-standing problem of Yard's conjecture. And he is a clear research fellow. And after his PhD, he has been very productive and resolved one problem after other. So today, he's going to tell us the complexities of minimum hypersurfaces. Anton, it's yours.
Thank you very much for the introduction. I'm very happy to be speaking at this conference. So I want to talk about complexities of minimal hypersurfaces and some quantitative estimates about these complexities. Let's see. All right, so the organization is going to be simple. I'm going to start with some motivations. There are going to be mainly 2 lines of motivations that I'm going to try to describe. And then I'm going to state the results and give you some ideas of proofs, because so the proofs are not so specific to minimal hypersurfaces, so might be of general interest. And in the third part, I'm going to talk about a general 2-piece decomposition for minimal hypersurfaces, minimal surfaces actually. And finally, I'm going to end with some related open questions. So let me start with the motivations. The theme today is to investigate the relation between so different kinds of complexities, so the measures of the size of minimal hypersurfaces, so volume, topology, Morse index, and singular set. So these are a priori pretty different kinds of measures of complexities, but they're very closely related. So one first big motivation for me to study this kind of questions was coming from min-max theory. I remind you that, so there's this min-max theory called Amgren-Pitts min-max theory for minimal surfaces that does the following. So you're given a closed Riemannian 3-dimensional manifold. Then the theory is going to produce for you a sequence of minimal surfaces that are really analogous to eigenfunctions of the Laplacian. And so, for example, generically, they are uniquely determined. So it's generically canonical. By generically, I mean for a metric G in a generic set of metrics in the sense of there. So based on questions and conjectures of Rick Shane, Fernando Cordon-Marquez, and Andre Neves, we conjecture that the genus of these min-max surfaces are going to be controlled by P. All right, so why is that a natural conjecture? So you have this sequence of kind of geometric eigenfunctions, and the question is, you want to control the geometry. So there's some natural control on other things, for example, the area or the Morse index that are coming from the min-max theory itself, very naturally, but there's no direct control on the genus. And because of many examples and partial results, the natural thing to conjecture here is that the genus of these surfaces, so these are embedded, closed, smooth surfaces, is controlled by P. And recall that there's a classical result of Schoen and S T that essentially says the following: if you're in a 3-dimensional manifold and your scalar curvature is positive, you're 2-sided, you're stable, minimal surface, actually you're topologically trivial, you're a sphere, a 2-sphere. So here we have something similar. You want to say that control on the index is going to control the genus of your surface. So what is known about this question? So first, in min-max theory, it's a variational theory. So you do have natural bounds on the Morse index of the objects you're producing. So Marcus and Neves, they already showed that for each p, you do some p dimensional min-max, you get a solution. The solution is a minimal surface, and you get what you expect on the Morse index, which is that the Morse index is always at most p, and actually generically it is equal to p. Chodosh, Montoulidis, and Sinjo, in their work on the multiplicity 1 conjecture in the context of minimal surfaces, they could prove that generically the genus is growing at least as fast as p, and also that the area of sigma p is p to exactly comparable to p to a certain power. So p to a power 1/3. And so here sigma p generically is going to be a multiplicity 1 smooth closed embedded minimal surface. More work related to that conjecture. So there's work of Savo, a lot of people. So Savo, Urbano, Ambrosio, Carlotto, Sharp, Borowski, Mendes, Radeschi, and they basically prove that the conjecture is true for metrics that are close to symmetric metrics. So they are using methods that require the metric to be close to being symmetric. And today we're interested in more general metrics. So sorry.
What does symmetric mean?
For example, symmetric means really round sphere or rank 1 symmetric spaces. So for example, Ambrosio, Carlotto, Sharp, the result is proving this conjecture for rank 1 symmetric compact spaces.
Okay. Thank you.
I'm going to say a little bit more about their method. But so the strategy for the conjecture should be clear. It's that we want to control the topology by the index. We already know that the index is controlled by p, right? That's the natural bound in the min-max theory. And so we want to focus our efforts on showing topology is less than the index. Okay, so that was the first motivation. The second motivation is coming from, the study of minimal surfaces with bounded area. There are many examples of minimal surfaces with bounded area. For example, in the round S3, there are these Laplacian surfaces. So Laplacian surfaces here, he produced for any genus many different minimal surfaces of genus G. And you can choose this sequence to have a bounded area. So what they look like really the singularizations of union of 2 equatorial spheres. So you have to imagine that you are in the round S3, you take 2 equatorial spheres that are intersecting along a circle. And what you can do is that you desingularize this circle of intersection by adding some holes. And you get these Laplacian minimal surfaces. Another construction still in S3 that's due to Capullias and Yang. So what they did was doubling of the Clifford torus. And what it means is that you are looking at the Clifford torus, you double it, and you try to add some small catenoidal necks between the 2 layers. And you hope that it gives you real minimal surfaces, and that's the case. So after that, quite a lot of people, so Capullias, McGrath, Vigul, and certainly other people constructed more examples with more layers. For example, doubling of the equatorial sphere, or you take the torus and now you have an arbitrarily large number of sheets that are connected by small necks. And these give you other examples of infinite sequence of bounded area minimal surfaces. And one question is the following: can one say anything general about minimal surfaces with a uniform area bound? The difficulty is that limits of these kind of objects, the limits of bounded area minimal surfaces, are very difficult to describe. It's not clear at all that they have more structure than just a general integer rectifiable stationary variable. So that's the question. Let me mention some kind of orthogonal works. For example, it's well known that Kolding and Miyakaze, they studied not bounded area, but bounded genus minimal surfaces. So their work, of course, the difficulty is then to treat the case where the area is large. So they can give a quasi-complete description of minimal surfaces with a certain given bound on the genus, and also their limits. Similarly, so if you now require a uniform bound on the index, you can look at the work of Chodosh, Maximo, and Ketover. They give a kind of description of minimal surfaces with bounded index. And of course, these work are orthogonal to what is interesting us today. So today, what we want is maybe having an area bound, but the genus and the index can be arbitrarily large. Let me note an earlier result by Edgery and Mikalev. So what they showed was that if you look at family of minimal surfaces with a uniform area bound, actually the index is already controlled by the genus. So that's everything here I'm talking about is in 3-dimensional manifolds. The ambient dimension is 3. All right, so that was the second motivation. So I think I can state the results. The first result is about lower dimensional manifolds, and it's a bound on the Betti numbers. The setting is that you're looking at the closed Riemannian manifold of low dimension in the sense of min-max theory, so 3 to 7. Okay, and the theorem is saying that given any area bound, you have a constant such that for any minimal surface with that area bound, the sum of the Betti numbers is actually bounded by the index linearly. So it's important that it's linear. And moreover, in dimension 3, this constant, you can say something about this constant that depends on A. It depends linearly on A, and that is optimal. So, so in this last line, CA is less than a constant C times A for C that's depending only on the ambient metric. Right, so here it's really a bound, an upper bound of the topology. Here our interpretation of topology is sum of the Betti numbers bound on the topology by the index. And one remark is that the Betti numbers here, you can take them in any field, over any field. That doesn't really matter. So let me know if you have any questions on the statements or what I said. One corollary, so two corollaries, but the first one is that in dimension 3, if the area is uniformly bounded, then actually the index and genus are pretty much equivalent. So that really comes from the previous results. So why? In dimension 3, the result says that the sum of the Betti numbers, that is the genus, is less than a constant times the index, right? And remember that Edgery Mikalev showed that the index is less than the genus. And so that means that in dimension 3, if you have a uniform area bound, you can think of the index as exactly the genus, like it's measuring essentially the same thing. That's one corollary. The second corollary is more related to our first motivation, which is that in dimension 3, you look at this min-max sequence of these geometric eigenfunctions, so these minimal surfaces sigma p. Remember that it is conjectured that the genus is at most p up to a factor, and a consequence of the previous theorem says that the genus is at most p to a certain power, 4/3. So it's not too far from 1, it's not 1. So why is that a consequence of the theorem? Let's see. Remember that here in dimension 3, the theorem says the genus is less than a constant times the index, and the constant itself is less than just a constant depending only on the ambient manifold times the area bound. But the area in the min-max sequence, the area in the min-max sequence is actually of the order p to the power 1/3. So at the end of the day, you get that the genus is going to be bounded by constant times the area times the index, and that gives you the power of p. So p to the power 4/3. And one remark is that the theorem 1 is a quantification, if you want, of compactness results. That's one way of interpreting the results. So compactness results of Schoen-Simon and Sharp, for example, who proved that bounded area and bounded index implies compactness, at least in the sense of varifold. So that's the first theorem, and it's a theorem about lower dimensions. You have a bound on the Betti numbers. But what about higher dimensions? Then I do not know how to bound Betti numbers. I think it's even false, actually. But you can still bound something. You can bound the size of the singular set. So now the setting is that you have a closed Riemannian manifold of dimension at least 8, and the natural object that you want to consider is minimal hypersurfaces with a possible singular set, because even minimizing currents in a higher dimension have singular sets of codimension set. And what you obtain by min-max theory, similarly, you're going to get minimal hypersurfaces with a small singular set of codimension 7. So you want to control that singular set in terms of the index. And that's exactly theorem 2. It's very similar to theorem 1. You're given an area bound. There exists a constant, so that for any minimal hypersurface that is smooth outside of a codimension 7 set, and with this area bound, then the n-7 Hausdorff measure of the singular set is bounded by the index to a certain power, which looks funny, which is 7/n. All right, so in higher dimension, there's a big difficulty, which is really people lack examples. There's really few examples of minimal hypersurfaces with singularities, even though we know that they exist, but the known explicit examples are basically perturbation of conical singularities, if you want. So that's why I'm not at all able to show, for example, that this is sharp, even though I think from the proof that it has a good chance of being the sharp bound. So this power of 7/n. So that's really the analog of theorem 1, but for the singular set and in higher dimension. And the remark is, what is this theorem quantifying? This theorem is the quantification of results of Neighbor Valtorta. So Neighbor and Valtorta, what they proved was that bounded area plus stable means that the n-7 Hausdorff measure of the singular set is uniformly bounded, right? Uniformly bounded. So here, it's a version for higher index minimal hypersurfaces. So do you have any questions on the statements? All right. If not, I'm going to give you some ideas of proof. For example, let's focus on theorem 1. I remind you that theorem 1 is, okay, so you want to bound the Betti numbers by the index linearly, okay? And so for previous work on this kind of question, so bounding the topology by the index, all these previous works, I think all of them are based on an argument of Antonio Ross. It's a beautiful argument using harmonic 1 forms. And what Ross did was he realized that you can bound, of course, the genus by the dimension of the space of harmonic 1 forms. That's fine. But for minimal hypersurfaces, you can also bound the dimension of the space of harmonic 1 forms by the index when the ambient manifold is nice enough. So intuitively, for each harmonic 1 form, you want to construct a corresponding variation that is going to contribute to the index of your minimal surface. Minimal hypersurface, sorry. So in this talk, everything is codimensional 1. It's always hypersurface. Right, and so that's the idea of Ross. But the problem, not the problem, but it really requires that the ambient manifold is close to being symmetric. You can protrude a little bit, but you need the metric to have some symmetries. So we want to do something different, and it's going to be via covering arguments and counting arguments. So it's more combinatorial in nature. And so let me give you a few words, give you a few ideas about how it works. So for example, we focus on dimension 3, we're supposing an area bound. And we want to prove something like genus is less than the index. The first thing to remember is a kind of epsilon regularity theorem that's due to Schoen. So Schoen, he proves that if you're stable in a ball of radius 2r, then you have curvature bounds and thus topology bound on the smaller ball of radius r. So that's a typical epsilon regularity, and this is the version for minimal surfaces. And that means that if you know that you're stable in B2R, then the genus, for example, inside BR is completely null. Remember that we have an area bound here. So the next step is that using a simple Bezikovich covering argument, you can find some disjoint balls B1, B2 until Bn, which are of the form BRP, such that the genus of your minimal surface is more or less bounded by the number of such balls, by n. So that's not hard. And you don't want this n to be arbitrarily large. I mean, it doesn't make sense to take n very, very large and all these B1, B2 very small. So you want to minimize the n, take the biggest BI possible. So you choose the radii of the BI so that sigma is barely stable in B2R, but it's not stable in B3R, right? So in other words, you make sure that when you construct these balls, you want sigma to be stable in 2 times bi, but not in 3 times bi. 3 times bi is just the ball that has the same center as bi, but is 3 times larger. Okay, and so because with that size of ball, you have the best of both worlds. So I'm going to say what it means. What you would like is that this number of balls is less than the index, because if it's true, you're done. The genus is less than n is less than the index. Remark that if all these big balls of 3 times bi were disjoint, that inequality would be trivial, because by construction, by choice of the radius, sigma is unstable in these big balls, 3bi. So if you have n disjoint sets where sigma is unstable, you have, by additivity, you have that they all contribute separately to the index, and then you have that the number of such subset is less than the index. But the main difficulty is, of course, that in general, these bi are not going to be, the 3 times bi are not going to be disjoint. And the bulk of the proof is about finding enough disjoint balls of the form 3bi. Remember that these bi, they're all disjoint, but you can easily imagine examples of larger and larger families of bi's that are all disjoint, such that none of the 3 bi's are disjoint, actually. And so I'm not going to say a lot more about the concrete way of finding these 3 bi, but let me give you some just intuitive picture. You have so you have disjoint balls. You know that they're all disjoint, and you want to find disjoint balls that are 3 times larger and same centers. And what I show basically is that if that's not true, then you have some concentration phenomenon. So you can imagine that if you cannot find a large number of disjoint 3 times bi, that means there's some large number of 3 times bi, okay, intersecting each other and having smaller and smaller radii and converging to a point. But that, by monotonicity formula and curvature bounds, that exactly means that in this region, your minimal surface is looking like planar analysis. And a good thing about planar analysis is that it doesn't contribute to the genus. So you could actually have discarded these balls in that argument. That's technically the way that you want to do. So to summarize a little bit quickly the argument, in order to find these disjoint balls, you have to edit those balls that are not contributing to the topology, that are not detecting really the genus. All right, so it's a counting argument then. What about higher dimension? Actually, it's extremely similar. Formally, it's almost the same. It's just that neighbor about torta, the result about the size of the n-7 Hausdorff dimensional singular set is replacing the Schoen-Simon bound. Remember, so Schoen-Simon is an epsilon regularity for stable minimal surfaces. You can interpret the neighbor about torta bound as a kind of similar bound, but for the singular set of stable hypersurfaces in higher dimensions. And you replace that in the argument, you run the commutator argument, you get at the end of the day a bound. Instead of the topology, you get a bound on the singular set. Is there any question about that? It was a little bit fast, I think. So let me maybe try to explain the power 7 over n because it's at first it looks a bit weird. So actually this power comes from the scaling and the harder inequality. So you in the proof, what you get is that the n-7th Hausdorff measure of the singular set is, by this covering argument, less than the sum of certain radii to the power n-7. So the power n-7 is just because of scaling and because of the Neighbor-Valtorta result, right? And then you can apply Hölder inequality. What you get is this product. And you see appearing two factors. The first factor is just the number of balls to the power what you want, 7 over n. The other factor is something else, but what's inside the bracket is the sum of the radii to the power n. And what's great is that these balls BK are, because they're disjoint, so this sum of radii to the power n is actually bounded by the area of your minimal hypersurface by monotonicity formula, for example. So the last factor is actually bounded by the area bound uniformly. So, and moreover, that's due to the counting argument, the number of the balls BK is comparable to it's at most the index, basically. That's the difficult part, but I claim that this is true. And then you get exactly this funky power of 7 over n. So the singular set is bounded by the index to this power. Right, so, but the point to remember, I guess, is that whether or not it's in higher dimensional or dimension, you have this general combinatorial and counting argument that gives you a bound on something, either it's the topology or the singular set by the index. That's the point. All right. Okay, so let me move on then. What I want to talk now is about is a kind of general two-piece decomposition for minimal surfaces. So, and that's something that is suggested by the proofs of theorem 1 and 2 that I just talked about. And what is this two-piece decomposition? So you're in dimension 3, you fix an integer, a large integer, and 0. And what you can do is that you can decompose any minimal surface sigma into two pieces. The first piece is called the sheeted part. Is the sigma larger than n0, and the second piece is the non-sheeted part, and I'm going to denote it by sigma less than n0. And this notation is to make clear that there's a complete analogy between this decomposition and the usual thin, thick, thick, thin decomposition for, say, hyperbolic manifolds, Einstein manifolds, or manifolds with bounded sectional curvature. So we have this, this analogy. Remember that, say, for hyperbolic manifold, you are fixing a scale, epsilon, and you say that you are in the thick part if your injectivity radius is larger than this given number, and you are in the thin part if the injectivity radius is smaller than your threshold. So what plays the role of the injectivity radius for minimal surfaces? Actually, the natural scale is going to be the stability scale. And this is the scale that we can define as follows. So at P, given the sigma is the minimal hypersurface, minimal surface, the stability scale is just the supremum of the radii, or such that sigma is stable in the ball of radius 2r centered at P. So for each P, you have such a number, you can check that it's a continuous function, and it's the natural scale that appears in the proofs that I mentioned before in the counting argument. When you want to construct balls in the covering, these balls are actually of size of the stability radius. And once you know what the stability radius is, it's just the smallest radius, the largest radius where you're still stable. You can define the decomposition. So for example, the sheeted part is just going to be all the points in your minimal surface such that on the scale of the stability radius, you have more than n0 components. So you have a lot of, so remember that by Schoen, the curvature bound of Schoen is independent of the area. So you know that at this scale, you always automatically have the associated curvature bound. Okay, so having more than n0 components is basically equivalent to saying that at this scale, the area, the rescaled area is very large. And similarly, the non-sheeted part is going to be the set of points, the complement set. Okay, the set of points where at this scale of stability, you have less than n0 components. And to continue with this analogy with the fixed in decomposition of hyperbolic manifold, this non-sheeted part is corresponding to the thick part. It's where the geometry is completely bounded, completely nice, by bounded and controlled by the radius. And you have the sheeted part, which correspond to the thin part of, say, manifolds with bounded sectional curvature. And this is where the situation is less controlled. It's not locally controlled by the radius. And so the point of such a decomposition is that it's something that holds for any minimal surface, whatever its area. And what you can do is then you can try to say, well, in this decomposition into two pieces, for one piece is the sheeted part, it's complicated, but you know that locally it has a lot of sheets, and you have the non-sheeted part that you would like to control. You know that locally you have very few sheets. You want to say something global about this non-sheeted part. So the non-sheeted part is again sigma at most n0. And the result here is that you can indeed do something like this, and you fix the threshold n0. What you have is that the area of this non-sheeted part is controlled by a power of the index, and the genus 2 is controlled by a power of the index. And these are the expected index. Right, so these are the expected powers. And the remark that I want to make here is, okay, so the symbol less than or equal to, of course, it's up to a factor, and this constant factor is depending only on the ambient manifold and the threshold that you impose, n0. It is independent of the area, that's the whole point. And the non-sheeted part, roughly speaking, you can think of it as behaving completely as a well-distributed minimal surface. By well-distributed, I mean, for example, look at the triply periodic minimal surface in Orth3. That's the typical well-distributed minimal surface, in the sense that now we can rescale down this triply periodic minimal surface, and you rescale, you get the sequence of minimal surfaces in R3 that become denser and denser in a very well distributed way, right? And you can check that in that situation, the non-sheeted part is the whole minimal surface. Okay, you have to choose an N0 fixed but very large, maybe 300. This N0, you look at this sequence of triply periodic minimal surface that you rescale. So the area locally is blowing up, things are getting denser and denser, but you can check that the non-sheeted part of such minimal surfaces is actually the whole minimal surface. And also in that case, it's pretty easy to show that locally the area is behaving as index to the power 1/3, and that the genus is behaving like the index. If you don't want non-compact things, you can just take the quotient, and now you're in a flat torus. You have a sequence in the flat torus. You have a sequence of minimal surfaces getting denser and denser, and it's an explicit example of where this theorem is sharp, basically. So this is the meaning of this theorem, right? Meaning that for any minimal surface, you have actually two parts. One part is behaving really like equidistributed minimal surfaces. The other part is very sheeted. And I want to also mention that this is false if you replace this non-sheeted part by the whole minimal surface. It's just not true. And the proof of that is, again, using the same kind of combinatorial arguments, but it's a more localized version, meaning that the condition on the non-sheeted part, so the condition that locally you can only see N0 components, this plays the role of the kind of area bound. And so you can localize all these techniques to the non-sheeted part that behaves at the end of the day like a minimal surface with an area bound. So that's a little bit the gist of it. Let's see, do I have something more to say? Right, so let me move on then to some questions. So the thing about questions, I really wanted to write down some questions because I feel like at least in my field, people are reluctant to write down questions in papers. And of course, there are open questions that are written, but to be honest, like 80% of them are coming from two people, like Yao and Ramon, and I'm sure that by hearing Yevgeny's talk and my talks, you will agree. So it's not such a good situation for many reasons. The most prosaic reason is that they only ask the finite number of questions, right? So here's my little contribution to this issue, and I'm trying to give you some very concrete questions, but that I cannot solve. So the first question is actually conjecture, because I'm pretty confident it's true. It's that in dimension 3, you have a general relation between area, genus, and index that's essentially optimal. So in dimension 3, what you want to prove is would be something like this. For any closed minimal surface, maybe embedded, the genus and area is more or less equivalent to the index plus area. The genus, if the scalar curvature is positive, the genus plus area should be equivalent to the index, and if the Ricci curvature is positive, the genus should be equivalent to the index. And so that means that you don't need to remember the explicit form of these relations, but the point is that for minimal surfaces, we have a very explicit and complete expectation of what should be the relation, the optimal relation between area, genus, and index. a couple of historical remarks. So Edgery and Mikalev actually showed in the first line, they showed half of the inequality already. I already mentioned their work. And so I write it as an equivalence just to make it look easier to read. Choi and Shane, what they proved was in positive Ricci curvature, half of this equality is true. And actually, that means that this conjecture in the case of Ricci positive is just a reformulation of a conjecture attributed to Shane and explicitly asked by Marquez and Neves. So that's good. And that's in dimension 3, meaning in dimension 3, because of a lot of examples, we know that these relations, if true, are sharp, are up to the constant factor, they are completely sharp. But what about higher dimension? Well, what can we say about higher dimensions? So that's my next slide of questions. And there I'm only stating them as questions. And it's going to be about stable hypersurfaces. So remember that in our arguments, we need as a starting block, as a starting point, some very solid knowledge of stable surfaces, stable hypersurfaces. So once you know what's happening for stable hypersurface, either using Shane-Simon or using Neber-Bautorta, you can somehow patch these estimates together to get something more global and telling you something about any index, right? But the starting block is really what's happening for stable hypersurfaces. And so that's why you need to understand stable hypersurfaces, especially when the area of these stable hypersurfaces get large, because usually all the results for stable hypersurfaces about singular set, about curvature, they only hold if you have a uniform area bound. You don't really know how it behaves when the area bound is going to infinity. All right, so what's the setting for the questions I want to ask here? To make it simple, look at the Euclidean space. You have the ball of radius 2, you have a stable minimal hypersurface of dimension n, right? And of singular set, maybe of codimension 7, okay? That's the setting. The first question is what's happening in lower dimension? And my guess that maybe the topology is bounded linearly by the area. That's a naive guess because we have so few examples, but it seems that the sum of the Betti numbers should be linearly bounded by the area of your stable minimal hypersurface that you started with. That's one guess. And the second guess is that in higher dimension, similarly for the singular set, the n-7 Hausdorff measure of the singular set of your minimal surface inside the ball of radius 1, that should be also bounded linearly from above by the total area of your stable hypersurface. So if true, that would be, of course, really interesting. So it's reminiscent, this kind of questions, of course, it's reminiscent of, I'll say, questions of Yau, conjectures of Yau about nodal sets of eigenfunctions, right? You want to bound some geometric quantities by other quantities. So I think it's essentially all I had to say today, all I wanted to say today. So feel free to ask questions.
Okay, thank you very much. So now it's time for questions.
Hello, Song. I have a question
Hi.
about the sheeted part. Because you have control on the non-sheeted part. I mean, for the sheeted part, should it be as bad as it can be? Like even if we have additional information on the metric.
So for the sheeted part, all that I can say is that by definition on the scale of stability, you have a lot of sheets. The problem is you don't really know what is going to be the interaction between, for this part, between area and index and genus. So you do have examples of sequences of stable minimal surfaces that are going to be very sheeted because there are some rather simple example in torus. So you have some stable tori of larger and larger areas, and they're going to be more and more sheeted. So that's something to have in mind. This is something that happens. And also you can make the genus also be larger and larger. So you have sequences, all the examples of sequences of large genus, larger and larger genus, stable minimal surfaces. In that case, the sheeted part would be at the end of the day, the whole minimal surface. It's really hard to say something about this part.
Okay, thank you.
I wanted to ask, suppose we look at the Gauss curvature. So suppose we are in dimension 3, we have a 2-dimensional minimal surface, we look at the Gauss curvature, right? Mm-hmm. Is it interesting? So suppose you have some sequence, then you sort of, well, you know, by Gauss-Bonnet, I don't know, if the genus is bounded, then you should have, is it interesting to see how asymptotically the Gauss curvature looks kind of as a function on a surface? Maybe do some rescaling or something like this.
Yeah, no, that's a very good question. So when I said that I was considering volume, like area, Morse index, or genus, so total curvature is definitely also something that you want to study, and it's related to the genus and the area by the Gauss-Bonnet formula. But so the thing is, you also have, say, an epsilon regularity for the total curvature. So you also can hope to run this kind of argument for the total curvature. But I'm not exactly sure what kind of result you would get for the total curvature. Yeah, as a first step, I studied the genus.
I see. Yeah, no, it's because you know, if you look at some sort of Laplace eigenfunctions on a surface, they become uniformly distributed sometimes, and sometimes not. Sometimes they concentrate somewhere. So I don't know. It's like how the scalar curvature behaves in some limit, but yeah, I don't.
You mean the total curvature?
No, just scalar curvature is a function on a surface. So
yeah, I see what you mean. Oh, the scalar curvature of the minimal.
Maybe not the scalar. Sorry, not necessarily the scalar, but the sort of the induced Gauss curvature.
Okay. Yeah. Okay. I've never really thought about the intrinsic Gauss curvature of the surface itself and how it concentrates.
Yeah. No, I'm not sure if maybe it's be good for something, but I don't know exactly.
Sorry, I have one more question.
Sure.
So in the conjecture slide in dimension 3, you have 3 conjectures. Can we go to, okay. So here, if we, let's say you have more information, let's say the metric is hyperbolic, that's the most generic case in dimension 3. And also, let's say the minimal surface would be, if it's stable and incompressible, we know that genus is controlled by the area. So here you just mean close, not necessarily embedded, probably immersed, and also we don't have any control on topology a priori. Maybe it's like a compressible, whatever. So is that correct?
Sure. But so here, in order for this to be true at that level of generality, you need, for example, in this line, I said genus plus area is equal to index plus area. So for example, when you say minimal surface given by incompressible surfaces in hyperbolic manifold, you would have that genus is more or less the area, the index is 0, so it's the area is equal to the area. So this is a little bit empty here, right, in that context.
And so for example, if you look at like surfaces which come from results of Cannon-Markovich, that would be an example, right? I mean,
right, exactly. And in that case, the area and the genus going at the same rate to infinity, but the index is 0. So okay, that equality is just area equals area.
Yeah. So this, okay.
Yeah. But that's an example to keep in mind. Also, again, I should emphasize that the last line is really a conjecture of Schoen and Marcus-Neves. Yeah.
There are any other questions? I have a question regarding, okay, anyway, any question, please go ahead. Okay, I have a question regarding the remark you made for theorem 2, as an estimate you had in theorem 2. And I think you mentioned that looking back to the proof you had, you think it's more or less quite sharp. The question is related to the ball you pick for the covering. So in the in your construction of the ball, or you choose a choice of the ball, so those balls, the geometry of the ball, you mean, are very similar.
Oh, are you
So
say that again?
The holder there. So once you use holder, and when in this estimate, in the proof, you right in this holder. So if geometry somehow the ball not that and the same, then holder you lose lots of stuff around this here. So I guess when you contrast this ball BK, and then probably the geometry, or at least the radius and the comparison should be very similar. So that's what you more or less you want to say, right?
I'm not sure I understood the.
So then for the first line to the second line, you want to use holder, right?
Yes.
So then, because it's more or less you want to compare, and you want to use the area of BK because you more or less use holder.
Right.
Once you use holder, then geometry of each BK, you want to indicate those. This is sharp, then the geometry should be similar. It's a different.
Yes. Yes. So if you're talking about this this last power,
yes, yeah.
So you have this power and you need to argue that okay, this because the BK are disjoint, and also because you're basically stable in 2 times BK, the sum is bounded by.
No, this part is okay. The part is from the first line, from the second to the third, inequality. When you use holder. So when you use holder, you lose a lot of information unless the second and the geometry of radius.
Okay. Sorry. Yeah. Now I get what you mean. Yes, sure. You lose a lot of it's if you have typically you have balls of extremely different size, and so typically this inequality is extremely non-optimal. It's extremely non-optimal. But the thing is that I expect having some examples where the size of these balls are all comparable, not too different.
So when you are picking those BK, you probably making very careful choices, such that there's a geometry when you do that kind of holder.
Sure.
Okay.
Sure. And in particular, in general, these BKs are going to be of completely different size. So this inequality is going to be completely close to optimal. Yeah.
So I think that for that part, more or less you want to use then in the stable case you want to use the area more or less is summation of in the case whether you had.
Right.
Okay.
And can I? Could you go back to the to the questions at the end about no, sorry, this about the area and the genus.
Yeah, sure.
So my question is somehow you can look, so or you know that on any manifold you can have metrics with very, very negative scalar curvature and also sort of negative definite reaching and things like that. So then probably the, so my question is, how will various bounds depend on the geometry, right? Because I don't know, you can take a like a free sphere and put a metric with extremely negative scalar curvature. So then probably the bounds, some bounds should look a bit different from the bounds on the round metric on the free sphere.
Right, right.
And so I don't know. I mean, one slight, you know, way of like quantifying this thing is that I like is you take conformal Laplacian and count how many negative eigenvalues you have. That's like one way of measuring, but maybe there are some other, you know, very nice ways of doing that. So the question is sort of if you fix topology, but then you start moving the metric, how will various things depend on the metric and maybe some geometric assumptions on that? So I guess.
Yeah, so maybe there's a way of measuring the negativity of, say, Ricci curvature by looking at how many stable minimal surfaces you have. That's a good question. Because in Ricci positive you have 0, but maybe you have some kind of quantitative, as you said, version of that for say negative Ricci on the manifold. So definitely the geometry, the curvature is going to influence it, but I'm not saying anything about the negative case because
yeah, but somehow, for example, in dimension 3, right, having positive scalar curvature is kind of difficult and tough, and kind of examples are fewer and far in between. But negative is more typical. Yes, so I guess trying to sort of, like you said, trying to measure negativity, you know, by counting minimal surfaces or something could be interesting.
Right, that's definitely an interesting question. Yeah, I haven't thought about that.
Yeah, no, I just, if it could be related to some sort of spectral things, that could also be interesting. I don't know.
Any other questions?
May I ask a question?
Sure.
Do you hear me? One of the motivations you have for like starting studying the problem is the algorithm pits min max. So you obtain that sequence of minimal surface, and you want to obtain a bound on the genus of that surfaces.
Right.
So I was wondering if you expect there is a proof like specific for that situation. Yeah, some other proof that not a general bound, so index bound the genus, but like some different proof of the genus bound in that situation.
Yeah, that's a very good question. So here the approach I'm taking is the general approach of bounding for any minimal surface genus by index. But as you said, the min-max sequence is a very specific kind of sequence, and it may be completely possible that using very arguments that are specific to the way you construct these minimal surfaces, you can get some improved, stronger results. I thought a little bit about that. I wasn't very successful, but I definitely think it is a possibility that you can use directly the way this sequence is constructed instead of having some general
result.
Yeah.
Okay. Yeah, thank you.
More questions? If not, let's thank Antoine again for the beautiful lecture. His next lecture will be on Friday, 3 p.m. Hope to see you all there then. Thank you very much, Anna.